Good afternoon already. Time is passing, and I'm promising to speed up to have you closer to the lunch. Thank you also very much for the possibility to present here today. I want to talk today a little bit about polyamide in flexible film applications. And polyamide is used very much for vacuum packaging, mostly for food which contains protein like all cheese and meat-based food products, mainly due to its combination of barrier properties, of mechanical strength, of transparency, thermoformability, and also thermal resistance. Polyamides are synthetic materials that have been developed in the time of starting 1938. Simultaneously, the polyamide 6 under the brand name Perlon, nylon 66 as the nylon brand name by DuPont. However, there are also naturally occurring polyamides. The protein main component of silk, wool, and others is a polyamide 2, is a nylon material. So these synthetic materials, which are thermoplastically processable, have then found first applications in the fiber area, later also in the film business. Polyamides are polycondensation products made from amine and acid. They have the amide reaction group as the constituting unit in the polymer chain, separated by olefin-like CH2 groups. The amides develop very strong hydrogen bonds, which create high intermolecular force and are responsible for the high properties like barrier and mechanical properties, but also for the water absorption of the polyamides. Most important polyamides that are used in the packaging field is polyamide 6 and also the random copolymers of 6 and 6,6 with a low melting point, which make up for about 10% of the polyamide consumption in packaging film applications. When looking at the processing of polyamide for film, the first points to come to, even before making the film, is its water absorption. Polyamides do absorb water, about 3% in standard air condition, about 9% when immersed into water. Polyamides needs to be dry at the time of the processing. Even pre-dried material which is exposed for a too long time to humid air will within a couple of hours absorb such a moisture level that it would cause smoke degradation, molecular degradation, and finally steam bubbles in the film that is extruded from that. Most polyamides are supplied pre-dried and needs to be protected from humidity until the time of processing. Then coming into the extruder, generally standard extruders of about the same configuration as used for polyethylene or polypropylene extrusion are used also for polyamide, usually with a relatively short compression zone of about a compression factor of 3. Generally standard extrusion lines can be used for polyamides too. Universal screws are applied in many cases. Temperature profile, of course, is much higher than in case of polyolefins. Temperatures range in the area of 260-65 for cast film, about 250 more for the blown film area, starting temperatures may range even in the area of 270-75 for the feeding section. When polyamide is extruded, it gets a lot of its property profiles from its crystallization, and polyamide is a material of an intermediate crystallization speed, unlike material like high-density polyethylene, which would crystallize very fast. On the other side, a PET crystallizing rather slow. polyamide is in the middle area with a crystallization speed to tailor the degree of crystallinity in a wide range by shock cooling, shown on the shown on the right side. A pretty amorphous film can be obtained by quenching the film so fast that it has no time to form crystals while in the temperature range where the crystallization speed is fast. Or on the other side, by cooling relatively slow, permitting a long residence time in the area in the range of crystallization, a highly crystalline film with visible crystals is produced. Polyamide is both produced by cast or by blown film. By standard technologies, in cast film, the film is extruded on a chill roll, which may be at a temperature about 20 to 30 degrees for soft thermoformable film, or at very high temperatures, even above 100 degrees for monolayer CPA lamination film. Important in the application of multilayer film is to have a viscosity match between the polyamide and the other components, polyethylene, polypropylene, EVOH, tie layer. The low viscosity component will go preferably to the edges of the cast die, as shown, as shown in the bottom film, where the low viscosity polyethylene is enriched in the edges and the higher viscosity polyamide is concentrated in the center, whereas with the viscosity match between the components, the polyamide and polyethylene thickness is more or less uniform across the width of the cast die. Blown film is also used for manufacturing polyamide and polyamide-based multilayer film. State-of-the-art equipment with IBC, refrigerated air. In many cases, especially for higher thicknesses, random copolymers are used for this technology due to their better processing in combination with a slow cooling rate of blown film. A problem that's occurring very frequently in case of non-symmetric film, non-symmetric multilayer film, having polyethylene or polypropylene on one surface and polyamide on the other surface, is the curling, the rolling of the film, which may be the converting of such a film difficult or impossible. This curling is created by the different crystallization kinetics of the materials. When the film comes out of the die, the polyamide as a high melting material will crystallize first. Much later will be the crystallization point, the frost line of the polyethylene. As the polyethylene shrinks in the time of the crystallization, the film will be rolling, will be too short to the side of the polyethylene layer. By passing the film through a hot water bath, a secondary crystallization of the polyamide layer can be induced. And if this secondary crystallization is just at the same magnitude as the first shrink of the polyethylene layer that had created the curl, then the film will be flat and no curl, even though it's a non-symmetric film. So this is a technology used by more and more blown film manufacturers to make pouch film with external polyamide layer, but no curl. A new technology that is coming up more and more is the water-quenched extrusion downward into a cold water tank. This is a technology that combines the very fast cooling of a cast line due to the high cooling efficiency of water in direct contact to the hot melt, with the advantages of a blown film, of being relatively flexible, having no edges, no edge trim, no waste from that. So it's a new technology to make a cast film-like material with a blown film line. with very good transparency, very good thermoformability, particularly in the area of rather high film thickness. And polyamide is also used for manufacturing of biaxially oriented film. It's transformed by all the three technologies that are available for biaxial orientation by the double bubble process for a blown film. The most common, the most frequent technology is the two-step or a sequential tender frame technology, where the film is extruded to a cast cylinder, then stretched in machine direction and finally in the transverse direction. And it's also processed by the simultaneous or one-step tender frame, where the cast pre-film is stretched simultaneously in both machine and transverse direction. And last but not least, polyamide is used pretty much for the manufacturing of sausage casing, today also mostly as a 5-layer multi-layer film, due to its shrinkability when processed in the double or triple bubble technology, its good oxygen barrier, its meat adhesion, which makes it the internal layer which adheres to the meat inside the sausage, and also its good printability on the surface. Polyamide is in nearly all cases used as a multi-layer film, combining the properties of the polyolefin like water barrier and sealability with polyamide properties like barrier, heat resistance, thermoforming, and mechanical strength. Here a typical structure of a 7-layer film having polyamide, EBOH, and polyamide in the center. This film is stained with a red to yellow color to make the layers better visible, with polyethylene on the outside, tie layer slightly visible by a tiny absorption of the dye, and polyamide, EBOH polyamide in the core layer. So this would be a typical high barrier pouch film. The properties of polyamide, as I mentioned before, are mostly determined by the very strong interaction between the amide molecule, amide groups, which are the constituting component of the polyamide. They create very high melting point in the range of 220 degrees, nylon 66 even at 260, very good strength, abrasion resistance, quite a good barrier, good printability, high surface tension. The water that is absorbed by the polyamide due to its polarity brings in very high toughness and very good formability. This water is absorbed by the film within a very short time. Thin layer of film absorbs saturation amount of water within a few minutes, and the water is inserted into the hydrogen bond and is acting as a true plasticizer, depressing the glass transition temperature, the temperature where the polymer goes from the tough into the brittle state, down from 56 to about 0 to minus 10 degrees. So it acts as a true plasticizer, and by this water absorption, the polyamide gets all its flexible, elastic, and impact-resistant type of properties. This water absorption also causes a post-crystallization of the polyamide. So even if the polyamide is shock-cooled by a very fast cooling rate, as soon as the film will absorb water or is exposed to elevated temperature, it will increase its degree of crystallinity to the standard level of about 40 degrees. Many people ask then, why does the film not get hazy by this crystallization? Because crystalline film is considered to be hazy due to the crystals. I have some photos of a shock-cooled film on the bottom and slowly cooled crystallized film on the left top side. When looking with a higher magnification, we can see in the middle photo the spherulites, the crystals in the crystalline film. but when looking with the electron microscope on the very right side, then it's visible that both films, the crystalline, slowly cooled, but also the shock cooled, which is always considered, told to be amorphous, do contain a very fine crystalline size of microcrystals. Only by post-crystallization, by humidity or temperature, this microcrystallinity does not coagulate into the large visible spherulites, which are the crystals that are normally making the film hazy. So there is no amorphous film, polyamide film, except immediately after processing. Generally, the shock-cooled, very soft and formable film is in reality a microcrystalline film. Polyamide is used for a number of different properties, very frequently due to its barrier properties for all kind of processed food applications. The polyamide has some level of oxygen barrier. I must say it's not a high barrier material, it's an intermediate barrier. It has a dependence of the barrier on the ambient humidity. When coming to a very small level of relative humidity, the barrier in fact increases by about a factor of 2. The OTR, the oxygen transmission rate, goes down, remains on this good level until about 50 to 60% relative humidity, and then decreases again to about 4 times worse level. All in all, as I said, the polyamide is an intermediate barrier material. The polyethylene, polypropylene materials, polyolefin materials on the very top are no oxygen barrier material at all, with very high OTR levels. Polyamide 6 and also some aromatic polyamides with a little increased barrier are somewhere in the central level in the range of about 10. And the high barrier materials, EVOH, are still 1 to 2 magnitudes better. So this is the range of the high barrier materials. Polyamide is used where an intermediate barrier is needed, like cheese packaging area, or in combination with high barrier materials like EVOH, and then it is used for all other kinds of properties like heat resistance, mechanical strength, puncture resistance, and so on. Also, the aroma barrier is quite high for polyamide. This is particularly interesting to keep aroma substances within food, but also interesting to keep aromas outside of food from neighbor areas in the supermarket shelf to avoid cross-contamination with other food or non-food products. Polyamide is widely used due to its thermoformability, and it provides thermoforming packages with a very good thermoforming depth and a very good retainment of the residual wall thickness in the thinnest spots, which are at the corners of the thermoformed mold. Thermoforming shown here in a sample can be done with cast and blown film, maintaining high residual wall thickness, and some products like the Ultramid B33 SL have been developed to even further increase the residual wall thickness in blown film. A typical structure of a thermoforming film close to 200 micrometers with a polyamide EVOH polyamide barrier block in the center, external further polyamide layer which is only used for the heat resistance, a polyethylene layer in between to keep the central barrier block dry, and of course then polyethylene and sealing material on the inside of the film. Polyamide is in fact very often used simply due to its mechanical strength for all kind of large food containers, bulk packaging of food that goes into further industrial applications. Puncture resistance is a very important question for all kind of food which is sharp-edged. Here in Turkey, I would first of all mention the packaging of nuts, hazelnut, pistachio, and all these kind of food which have a lot of sharp edges, broken nutshell, which might easily penetrate the pouch. And we can see here that the water-cooled film is of a superior puncture resistance compared to other technologies. Due to its heat resistance, polyamide is used quite a lot for the external layer of film for running with a very high seal bar temperature. Typical structure for a high barrier laminated film would be polyester on the outside and then a very thin film, 7-layer, today even 9-layer film, having PA, EVOH, PA in the center, 1 to 2 micrometer only of PA, EVOH to provide a very high barrier. Let me summarize. The polyamide is used very much for food packaging, to be more precise, for vacuum food packaging, due to its combination of high mechanical properties, transparency, heat resistance in the sealing property, quite high oxygen barrier and chemical barrier, and its good thermoformability. A little overview and a little photo of the place where I'm coming from, where BASF is manufacturing these grades, and I thank you very much for your attention.